All right, I'm going to show an example of how a derivative can be used to estimate marginal revenue in a business type problem. The problem is the weekly revenue in dollars from selling X custom-made desks is, so the answer to this function, R, will represent the revenue in dollars for selling X desks. The problem, I'm getting this problem out of your textbook. It's number 11 on page 130, lesson 3.4. And this is the calculus book by Finney, DeManna, Waits, and Kennedy. And the first question is, draw the graph of R. What values of X make sense in the problem situation? I went ahead and made a table where I plugged in like 0, 1, 2 desks, 3, 5 desks, 6 desks. Plugged them into the function. It wouldn't make sense to plug in negative numbers for number of desks, and it wouldn't make sense to plug in any fractions or decimals. The types of numbers that need to be used would have to be whole numbers because they're numbers of desks. So the domain of the function, I guess the domain that would make sense in this case would be whole numbers, 0, 1, 2, 3, 4, etc. As far as drawing the graphs, I made the x-axis my number of desks, the y-axis, the vertical axis, my R of x-axis, and I plotted those points, and of course you could sketch in a curve. Now, keep in mind, even though this is going to be a continuous function here that would look something like this, in reality, we can't have 1.5 desks or 2.5 desks. Really, these black points are the points that are really meaningful to us in this problem, as well as, for example, there would also be points at 3 desks, 4 desks, 5 desks, 6 desks, etc. So even though we're modeling this with a continuous function, the graph would really be discrete if we wanted to graph it accurately. Discrete meaning that we cannot have any decimals or fractions in here. All right, to find the marginal revenue, which I think is part B of this, we need to find the derivative. The derivative is going to give us the marginal revenue. Marginal revenue is how much the revenue is going to increase when we increase the number of desks by 1 desk. Another way to look at that is it's the derivative. Okay, we're using the derivative to estimate the marginal revenue. So first of all, I could multiply through by 2,000 to get 2,000 minus 2,000 over x plus 1. That's just rewriting the function. I may want to change the minus to plus and negative 2,000. Now I'm going to do the derivative of my revenue function. This will be my marginal revenue function. The derivative of 2,000 would be 0. Over here, there's different ways I could calculate this. I'm going to go ahead and review the quotient rule and show you the quotient rule. So it's low, d high, minus high, d low, whoops, excuse me, and the saying I'm using to find the quotient rule is low d high minus high d low over low squared. It's a quick way to remember the quotient rule. So low is x plus 1, d high, the derivative of negative 2,000 would be 0, minus high, whoops, so it's minus negative 2,000, d low would be a 1 over low squared. So if you simplify that, that comes out to minus a negative, so that's positive 2,000 over x plus 1 squared. So my derivative, which is my marginal revenue function, is positive 2,000 over x plus 1 squared. That will give me the marginal revenue at x desks. So that's your answer to part B, where it says find the marginal revenue when x desks are sold. This is the answer. Part C, use the function r prime of x to estimate the increase in revenue that will result from increasing sales from 5 desks to 6 desks. So we're trying to estimate that when we go from 5 desks to 6 desks, how much the revenue is going to increase right here. So what we're going to do to figure that out is we're going to do an equation of we're going to find the slope of this tangent line, which is found using the derivative. So I'm going to plug a 5 into my derivative. So I'm going to find r prime of 5. That will give me 2,000 over 5 plus 1 squared. So that's 2,000 divided by 6 squared. 2,000 divided by 36 is $55.56 approximately. So we're estimating that when we go from 5 desks up to 6 desks, this has a slope of $55.56. Now remember, that means we could put a 1 under that. That means that for every 1 desk that we increase from 5 to 6, we increase 1 desk, we're expecting the revenue to go up by $55.56. Now, is that the actual marginal revenue? No, the actual marginal revenue could be found by subtracting these two. If you subtract $1,714.30 minus 166.7, you're going to get the actual marginal revenue we subtract these two values of $47.60. Our derivative is used to estimate that number. In this case, we got $55.56. On the picture, you can see the actual revenue, this distance, would be $47.60. But if you went all the way up to the tangent line, the actual revenue, or the estimated revenue increase would be this total distance here. So that would be a total of $55.56. So, good example of how, even though in this case we could actually find the marginal, derivatives can be used to estimate these values.